I'm going to introduce paper talk about the ones in prospect theory. So in this paper, the author created a new methodology called cumulative representation of uncertainty. Basically the goal is in class we know to value a lottery, we will sum over the decision weight and multiply by its value of a specific case. And but in the class, we basically treat the decision weight for different cases as independent case. But in this paper, the author proposed a method using cumulative function such that for different weight, for different case, the measure of weight are not independent. In the theory, we create a functional to represent a lottery. The function is from set of event to monetary outcomes. For example, for specific event happens, then the corresponding outcome, we measure that outcome use monetary value, and then the function will be from a set of events to set of outcomes. And we partition the set of events based on the order of the monetary outcome. So we order all the axes in X set from the lowest amount to the highest amount. So for gains we use positive number. For loss we use negative number, and we put this rank order with subscript to A. So A represents, so different A's here represent different event in the S set, and corresponding we will have here is n plus n pairs of event in this set, and so we want to create the lottery based on gains and loss. So because we know for gains and loss, people have different attitude to that, so we should have different measure of that. And the final goal is, remember, we want to create a value function V from all possible lottery to a real number. And this lottery is measures the exact order of which lottery is preferred. Okay, so for a lottery, we will separate it to gains lottery and loss. The case of gains and case of losses. So we will have two parts. We will sum these two parts together. And for each different component of this function, we will measure the value based on the same methodology as before. So to create to define a function of V, basically the task is defined of pi. So to define different of to make a different definition for positive for gains and loss, the task basically becomes to define the probability. How can we measure based on the probability? How can we measure the weight of decision based on the corresponding probability? What the methodology we use is called the capacity function. The capacity function is a set function like assign different set event with a real number. But what we can do is for different event happens, we want to measure the marginal contribution of a specific event, and we use that marginal contribution as the decision weight. So we will have for positive number, we will measure the marginal contribution to the capacity, and we will assign the worst case, the best case, and the worst case. We fix that, and then we can go to correspondingly measure the cases in the middle. Because we are dealing with lottery, so we can basically use the probability as a method to measure the set, to measure the probability to measure set. So we have a formula like this. This is the base. This is exactly the same with a different notation. And the following is an example. And we have suppose we have we roll a dice from 1 to 6, and of course if we can gain when we get a odd number. If we have an even number, we can receive X values. If we have odd numbers, we will lose X value. So based on this, we can measure what is the value of this lottery. And the value of the lottery will be, for even numbers, we will treat it as gains, but here for gains nothing, which basically means we don't have any gains. We treat the probability as 1/2. Similarly, for loss, we do the same thing. And we will add them up together. We'll have this formula. Then the remaining task is, how can we measure value V and W, positive W and negative W? So it means measure for decision weight, for gains or loss, and for each case is the value itself. For the value itself, we can use the prospect theory as we studied in class. But for decision weight, the author proposed this graph. This graph is constructed based on experiment. So the author collected 25. The data is based on 25 people in the past, and use that data to create this figure. In this figure, we can see the dotted line is for gains weight, gains decision weight. The dashed line is for losses decision weight. And if the probability closer to 1 and 0, we are more sensitive to that. So for 1, we underweighted the value. For 0, we overweighted. Remember, for specific cases, for specific case, we will have a marginal effect as we will do the marginal effect as the decision weight. Then the slope will be the value of the corresponding cases, the weight of the corresponding cases. So we can think of people will get more sensitive to worst case and best cases. For example, if people will get more sensitive to the highest gain and sensitive about against get nothing, and also similar for losses, people will get more sensitive to the biggest loss and sensitive to gain nothing, loss nothing. So we will but here we notice another thing is the gains is more, the bias for gains is more is more than the losses. So so it basically means the risk aversion for gains pronounces more than risk seeking for losses. So that's all the paper is saying. Thank you.